Okay, so hello everyone, welcome to my presentation. My name is Rabee Taha. I'm from the University of Duisburg-Essen, the Institute for Construction Management and Economics from Germany. And today I will be presenting the research that my colleagues and I worked on, which handles the topic of an investigation and analysis of the required BIM data for automated shell construction using a cable-driven parallel robot. So starting with the motive behind this research, now more than ever, the construction industry is in need for automation. This is caused by several factors, such as a growing shortage of skilled labor, stagnating productivity in the industry, higher construction costs, insufficient quality, and even longer construction durations. All of this together makes automation a necessity in the industry and no more a luxury. In order to counter these factors, we at the University of Duisburg-Essen, in an earlier research, verified the usage and the implementation of cable-driven parallel robots, short CDPR, to automate different construction processes, such as the construction of sand-lime walls and the construction of ceilings from wooden elements. And so this current study focuses on investigating BIM data integration that can enable this execution automation for the use case of building wooden ceiling elements. And the reason behind that is our earlier trials proved that this automated execution requires highly detailed 3D BIM data that should be translated into machine-readable formats with zero loss, with full integrity of the data. And despite it being feasible, achieving this seamless BIM to robot data flow still poses a challenge, particularly due to the information loss during IFC export. As you can see here, this is a visual representation of the CDPR system that we developed at the university. It basically consists of an end platform that is actuated by 8 cables. These cables are controlled through winches and pulleys. And the reason behind choosing this specific type of robotic systems is that these cabled robots actually offer benefits such as high precision, large-scale motion control, even with significant payloads. This makes it ideal for usage in the construction industry. And in an earlier project at our university titled On the Way to Digital Construction, we assessed how effectively BIM can supply task-specific data for this robotic execution to automate this execution process. But in this research, we wanted to dive even deeper into that. And for that, we developed a 6-phase framework to analyze this BIM data integration into the CDPR system. And the framework can be mainly split into 3 categories, each consisting of 2 phases. The first of which being data requirements and organization. The second, data preparation and modeling. And lastly, the validation and quality assurance. This framework actually supports and enables systematic BIM to robot translation through 4 key points. The first of which being targeted data extraction, structured classification of the different elements, a standardized IFC mapping, and technical quality validation. All of this, of course, with the objective being to ensure BIM data, BIM exported data, is explicitly defined and machine readable and interpretable for the automated execution. So diving into the first 2 phases, data requirements and organization, the objective was to identify, extract, and classify the information we needed to achieve this automation in the execution. And the way we implemented that is by analyzing the most key components for our use case, which in this case were ring beams, U-blocks, the wooden ceiling elements, and ceiling layers. And for these components, we then analyzed what the most essential parameters were for the robot to be able to execute this automation. And these were position, dimension, of course, material properties, and structural details. These identified parameters were then categorized into two categories, the first of which design-dependent parameters, the second component-dependent parameters, and these design-dependent ones are, of course, project-specific, so they vary from one project to another, which means we need to be able to handle them in a flexible manner, whereas the component-dependent parameters can remain consistent across projects, and they can ensure better standardization. Of course, the goal being maintaining property integrity during IFC export, which is critical for the robot to be able to perform this automation. These were the results of the first two phases. So these were the structural elements relevant for our use case. The ring beam, which was then specified into the components, U-bricks, concrete reinforcement, the ceiling layer, of course, and the ceiling elements. And for each of these components, the most important parameters were identified: position, dimension, density, direction, guide, the global unique identifier. And these parameters were then split into design-dependent, component-dependent. Position was more design-dependent, dimension the same case. Density is, of course, component-dependent. Direction, again, design-dependent, and the last two being component-dependent. After that, we come to phases 3 and 4, data preparation and modeling. And the objective was to map these Revit categories into the corresponding IFC classes, structures, enabled to enhance the consistency and the export accuracy. And to implement that, we did some specific export configurations, such as checking the checkbox for building story for all the relevant levels, and creating the model in an LOD 400 level of details, which includes geometry, material, and structural data. We then analyzed the whole modeling process, ensuring that the required attributes are generated and also stored correctly. This is the keyword here within Revit, with our focus being to ensure the availability of these attributes prior to the export in order to enable the machine readability. So the results of these phases, these were the specific components that we did this analysis for. This was the corresponding IFC classification for each of these components. And for each of them, we then did a small investigation whether their standard Revit libraries included sufficient information to include all the attributes we needed for this automation. For some of them, we needed to create manually our own libraries based on manufacturer informations. And then we moved on to the last category, the final two phases, which handle the last step before the execution, the export step. And our objective here was to ensure the data integrity and usability after this export process for the robotic automation. And the way we implemented that was by analyzing export settings for two different IFC formats, IFC4 and IFC 2x3, for each of which we experienced with two export trials with different export settings. And these trials were then reviewed through visual inspections and through attribute validation, including guides, classification codes, material specification, and of course, dimensional parameters. And the results of this analysis were the first IFC4 export with the standard settings. It was able to successfully transfer structure data, guides, and level hierarchy, but it showed some issues, like misclassifying some components. For example, the U-brick component was classified incorrectly, and we had a partial loss of properties, such as, for example, the material density, whereas in the second trial, with the user-defined export settings, we had no issues. The transfer was basically successful. It included all the key physical parameters, and even the brick was classified correctly, unlike in the first trial. This result was actually the same for the second IFC format, 2x3. And the conclusion was that trials 2 and 4, so basically the ones with the user-defined settings, showed the best results, the best accuracy, and validated export settings enhanced the automation readiness by preserving this data. To conclude, this is an overview of our whole methodology. We start out with a BIM model, which then goes through these 3 steps to ensure the integrity of the data, first by analyzing requirements and organization, then the preparation and modeling, of course at the end the validation, and then this data is communicated to the robotic setup, which performs the automated execution. And the study demonstrated that IFC can enable reliable BIM to robot data exchange, but that depends on configuration from the user and task-specific adaptation. And so a key recommendation that can be derived from this study is to develop a standardized IFC export profile that is tailored for such automated processes with robots to ensure the complete and loss-free data transfer. And of course, an ongoing debate to whether IFC is the optimal format, since there are other formats emerging, such as the USD, Universal Scene Description. And so a future direction for this research could be to explore this other format and to perform a comparative study between both to see which is more optimal for the robotic execution. With that, I come to the end of my presentation. Thank you very much for your attention.